Our entire universe was once smaller than a single atom. This is the story of cosmic inflation, the leading theory for our cosmic origin, and it will completely reshape what you think of as reality. By the end, you will understand how every galaxy, star, and planet grew from microscopic quantum jitters. How can everything we see come from almost nothing? And what does the oldest light in the universe reveal about our first moment? What does it mean that the cosmos itself might be built on a foundation of random chance? This primordial void was the ultimate blank slate, but calling it empty would be a profound mistake. It was a realm of pure potential, a seething ocean of energy so dense that our familiar ideas of here and there, before and after, simply did not apply. Within this chaos, a strange and powerful entity existed, known to physicists as the inflaton field. Picture the most turbulent sea you can conceive, where waves of raw energy constantly rise and fall, crashing into one another with unimaginable force. That was the state of the cosmos. The rules of reality were not just being bent, they were being written in that very moment, under pressures and temperatures so extreme that we can only recreate fleeting echoes of them in our largest particle colliders. This remarkable beginning raises a compelling question. Why did this chaotic sea not simply remain chaotic? The answer lies in a peculiar property of the inflaton field itself. It possessed a kind of tension, an unstable energy state that yearned for release. This instability made the subsequent explosion of growth, cosmic inflation, not just a random chance but a virtual certainty. To understand the mechanism of this great transformation, we must now introduce the mind who first conceived it. Alan Guth was working on a problem of subatomic particles when he stumbled upon a cosmic answer. He realized the early universe could have undergone a phase of breathtakingly rapid expansion, a growth spurt so intense it makes the later Big Bang seem almost gentle. This was cosmic inflation. The mechanism for this expansion was something truly unusual, a state of matter that generates a repulsive form of gravity. Think of it like this: if you were to stretch a rubber sheet, objects on it would move apart. Now imagine the sheet itself is not just stretching, but generating the force to stretch itself faster and faster. That is what space itself did during inflation. It was not things flying away from each other through space, but the very fabric of reality expanding, carrying the seeds of all future structure along for the ride. This single idea solved two profound mysteries in one elegant stroke. The first is the horizon problem. Why does the universe look so remarkably similar in every direction we look, even to regions that should have never been in contact? Inflation explains this by stating that these distant regions were once intimately connected, smaller than a proton, before the inflationary stretch pulled them apart. The second puzzle is the flatness problem. Our universe appears incredibly flat on large scales, a very specific and unlikely condition unless something guided it into that shape. Inflation acted like a cosmic iron, smoothing out any initial curvature and stretching the universe into the flat geometry we observe today. Guth's spectacular realization gave us the first coherent picture of our ultimate origin, a framework where the vast cosmos could emerge from a microscopic speck. But what was the fuel for this incredible transformation? What is the nature of the engine that drove this brief but universe-defining period of hyper-growth? This inflaton field was the engine of the entire cosmos, a fundamental presence that filled every point of that early chaos with immense potential energy. Think of it not as a substance but as a condition of space itself, like a vast, uniform slope that the universe was poised upon. this was a false vacuum state, a temporary yet remarkably stable plateau of high energy. And it was this unusual stability that powered the exponential growth. According to the principles of general relativity, such a dense, uniform energy state produces a surprising effect, a negative pressure that generates a repulsive form of gravity. Instead of pulling things together, this gravity pushed space itself apart from the inside out. The cosmic balloon analogy offers a helpful picture. You are not blowing air into the balloon from the outside. The rubber of the balloon itself is generating the force to stretch, and it is doing so at a rate that is almost beyond comprehension. The universe did not just grow, it doubled in size and then doubled again and again, in intervals so brief they are measured in fractions of a trillionth of a trillionth of a second. This relentless, exponential stretching is what smoothed the cosmos and made it uniform, explaining its large-scale structure. But this process was also storing energy on a truly cosmic scale. Every tiny region of space, stretched to an enormous size, carried with it the locked-in energy of that early inflaton field. The universe was being prepared like a spring, storing the potential that would soon be expressed as the heat and matter of the Big Bang. This field was not just expanding space, it was carefully setting the entire stage for the cosmos, creating a perfectly smooth and energized setting for the next great act. So what influence could possibly interrupt such a powerful and stable process, causing this field to finally release all of its stored energy and bring the inflationary era to a close? The stability of the inflaton field was not meant to last forever. It existed in a delicate state, like a ball balanced perfectly at the very top of a steep hill. The slightest nudge was all it would take to send it rolling downward. In the universe's earliest moments, that nudge came from the constant motion of quantum mechanics itself. A tiny, random fluctuation somewhere in the field caused a local shift, a small patch where the field began its inevitable transition from its high energy state down to its true, lowest energy condition. This change, which cosmologists call the Graceful Exit, marked the definitive end of the inflationary era. The great cosmic stretching was over, and in its place began a transformation of immense power. The vast potential energy that had been stored in every point of space, the very fuel for inflation, was now released in a spectacular cascade. This process is known as reheating. Imagine a landscape locked in a deep, universal stillness. For eons, it has been completely calm, holding a colossal amount of latent energy. Then, in an instant, the shift comes. Not as a gentle warming, but as a powerful, expansive release. The entire quiet surface transforms into a vibrant ocean of heat and motion. That is what happened to the cosmos. The energy of the inflaton field did not vanish, it transformed. It filled the newly expanded universe with a hot, dense mixture of fundamental particles, a brilliant primordial plasma of quarks, electrons, and photons. This brilliant moment is the true beginning of the hot Big Bang as we traditionally picture it. The vast, smooth, and open expanse left by inflation was now filled with the raw ingredients for everything to come. The precise mechanics of how this energy transfer occurred, how the inflaton field connected with other particles to create this rich mixture, remains one of the most active frontiers in theoretical physics. It involves complex interactions at energies we can only imagine recreating. Yet this reheating was not perfectly uniform. The quantum motions that started the transition were not smooth, and they left their mark. The hot mixture was not featureless. It was imprinted with tiny, random variations in density. These microscopic differences, stretched to cosmic proportions during inflation, were the seeds of all future structure. The universe now had its canvas and its first brushstrokes. setting the stage for gravity to begin its slow, patient work of cosmic construction. This cosmic transformation from a uniform sea of energy into a structured universe hinged on a single, beautiful imperfection. The very laws of quantum mechanics ensured the inflaton field could never be perfectly smooth and silent. A fundamental rule, the Heisenberg uncertainty principle, tells us that on the smallest scales, there is always a background fizz of activity. Energy is never perfectly fixed. It is constantly borrowed and repaid in an endless dance. For the inflaton field, this meant that tiny, random fluctuations were constantly appearing and disappearing, like momentary ripples on the surface of a deep ocean. These quantum jitters were the universe's first and most crucial brushstrokes. While inflation was stretching space itself to an unimaginable degree, it was also stretching these infinitesimal ripples. Think of drawing a tiny, wiggly line on the surface of a deflated balloon. As you inflate the balloon to an enormous size, that wiggly line is magnified into a vast, continent-spanning wave. This is exactly what happened to those quantum fluctuations. What began as subatomic ripples in the energy field were stretched by inflation to become astronomical in scale. As the era of hyper-expansion came to a close, these magnified ripples did not simply vanish. They were frozen into the very fabric of the newborn cosmos as slight variations in density. Some regions of the hot, dense plasma were now ever so slightly denser than others. These minute differences, these seeds of imperfection, were the reason our universe is not a vast, dark, and featureless void. They provided the necessary blueprint. Without them, gravity would have had nothing to grasp, no starting point from which to begin its patient work of pulling matter together over billions of years. Every galaxy cluster, every swirling spiral of stars, and every solitary planet exists today because of those primordial quantum jitters, the random static that became the signature of everything. These faint ripples in density were the universe's most important blueprint. After the fiery dawn of the Big Bang, the cosmos was a nearly uniform sea of hot particles, but it was not perfectly smooth. Those microscopic quantum jitters, stretched to cosmic proportions, meant that some regions were ever so slightly more crowded than others. This subtle unevenness was all the invitation gravity needed to begin its work. Over immense spans of time, measured in hundreds of millions of years, gravity acted like a cosmic amplifier. A region with just a tiny bit more mass exerted a slightly stronger gravitational pull, slowly drawing in more matter from its surroundings. Picture a very gentle, wide hill on an otherwise flat landscape. When it rains, water naturally flows downhill, gathering in the lower areas and making the hill even larger and more pronounced. In the cosmic context, the hill was a region of higher density, and the flowing water was the dark matter and normal matter being pulled inward. These growing over densities eventually became so massive that they collapsed under their own immense gravity, forming the first vast clouds of primordial gas, the protogalactic clouds that would later fragment into the first brilliant stars and the majestic galaxies we see today. Conversely, the regions that started with slightly less material, the underdensities, were steadily drained of matter. They expanded into the vast, empty tracts of space we now call cosmic voids, the great empty bubbles in the foam of the universe. This relentless gravitational sculpting, acting over nearly 14 billion years, is what transformed the faint, random whisper of quantum noise into the grand, organized chorus of the cosmic web, with its glittering galaxies, immense clusters, and sprawling superclusters. This entire process provides a direct, testable link between the unpredictable quantum realm and the majestic cosmos we inhabit. But a story this profound requires more than a compelling theory. We need to see the evidence with our own eyes, and that proof is written in the oldest light that still travels through the universe. This ancient light is our most direct window back to the universe's infancy. Known as the cosmic microwave background, it is the faint afterglow of the Big Bang itself, a fossil radiation that has been traveling across space for nearly 14 billion years. It was released when the universe was just 380,000 years old, a moment when the hot, dense plasma of particles cooled enough for the first stable atoms to form. In that instant, the fog cleared, and light was finally set free to travel across the cosmos. Today, this radiation fills the entire sky, a uniform bath of microwaves that is the cooled remnant of the universe's fiery birth. To our most sensitive instruments, however, this background is not perfectly smooth. It is imprinted with a specific pattern of incredibly faint hot and cold spots, temperature variations of just 1 part in 100,000. These minute differences are the cosmic blueprint made visible. Each slightly warmer patch marks a region of the early universe that was a little denser, a place where the primordial plasma was under higher pressure. Each cooler spot corresponds to a region that was slightly more rarefied. These are the very same quantum fluctuations, the microscopic ripples in the inflaton field, stretched to cosmic proportions during inflation, and then frozen into the fabric of reality as density differences. The statistical pattern of these hot and cold spots, mapped with breathtaking precision by satellites like COBE, WMAP, and Planck, is a perfect match for the predictions of inflationary theory. The characteristics of these ripples, their size and distribution across the sky, tell us not only that inflation happened, but for how long and with what incredible force. It is as if we had discovered the original architect's drawing for a vast city, confirming not only who designed it but the precise methods they used. This cosmic snapshot provides such overwhelming evidence that it solidifies inflation as the cornerstone of modern cosmology. It raises a profound and almost philosophical question, however. If our magnificent universe, with all its galaxies and stars, truly grew from random quantum static, what does that say about the role of chance in the very foundation of existence? The pattern of hot and cold spots in the cosmic microwave background is far more than a simple confirmation of ancient ripples. It carries a specific signature, a unique fingerprint that only cosmic inflation could have left behind. The theory makes a remarkably precise forecast about the nature of these primordial fluctuations. It tells us they should be nearly scale invariant. This means the pattern of ripples should look statistically similar, whether you are examining a large swath of the sky or focusing on a tiny patch. Imagine listening to a type of static that sounds identical whether you hear it for 1 second or for 1 minute. That is the kind of uniformity inflation produced. Furthermore, these fluctuations are predicted to be Gaussian. This is a statistical term meaning the variations are completely random in a very particular way, with no hidden correlations or preferred patterns. There are no cosmic orchestrations, just the pure, unpredictable fizz of quantum mechanics expanded to a universal scale. The stunning agreement between this prediction and the exquisitely detailed maps from satellites like Planck is a triumph of modern science. But the inflationary fingerprint holds another, even deeper clue. The theory predicts a specific relationship between 2 types of primordial ripples. The first are the curvature fluctuations, the density wrinkles that eventually seeded galaxies. The second are primordial gravitational waves, ripples in the very fabric of spacetime itself, generated by the powerful tremors of the inflationary expansion. The ratio between the strength of these gravitational waves and the density wrinkles, known as the tensor-to-scalar ratio, is a direct window into the energy scale of inflation itself. Detecting this specific signal is one of the most important quests in cosmology, as it would tell us exactly how powerful the inflationary engine was in those first fleeting moments. While we have not yet definitively measured this primordial gravitational wave background, the search continues with increasingly sensitive experiments. The cosmic microwave background provides a spectacularly successful test, but the evidence for inflation is not confined to this ancient light alone. The echoes of those first quantum jitters are woven into the very architecture of the cosmos we see around us today. We can see the legacy of those quantum ripples written across the night sky. The universe is not a random scattering of isolated islands, but a vast, interconnected cosmic web. Gigantic filaments of galaxies stretch across billions of light years, connecting dense clusters and wrapping around immense, empty voids. This is the large-scale structure of our cosmos, and it is a direct descendant of the microscopic density variations imprinted by inflation. This grand architecture is a fossil, preserved and magnified over nearly 14 billion years. To read this fossil record, astronomers undertake monumental surveys of the heavens. Projects like the Sloan Digital Sky Survey have painstakingly mapped the positions of millions of galaxies, creating a three-dimensional atlas of the local universe. When you look at the resulting map, the pattern is unmistakable, a delicate, web-like structure that mirrors the faint hot and cold spots in the cosmic microwave background with astonishing fidelity. The statistical clustering of galaxies, how they group together at different scales, is a perfect match for the initial conditions seen in the infant universe, just after gravity had 13.8 billion years to sculpt and enhance them. It is the ultimate confirmation of a cosmic life cycle. Imagine having a photograph of a person as a newborn and then comparing it to a detailed portrait of them as an adult. You would see the same underlying bone structure, the same fundamental features, just matured and defined by a lifetime of experiences. In our cosmic analogy, the baby picture is the cosmic microwave background, and the adult portrait is the galaxy map we see today. The agreement between them is not just consistent with inflation, it is a precise quantitative match that provides a second, completely independent line of evidence for the theory. This grand design is governed by a specific set of numbers, cosmic parameters that describe the exact amplitude and pattern of the initial fluctuations. Inflation not only predicts that these fluctuations should exist, but it also provides a compelling explanation for why these fundamental numbers have the specific values they do. They are not arbitrary constants, but a direct readout of the energy and duration of that first, explosive moment of growth. The geometry of our universe is a perfect flatness on the grandest scales. The angles of a triangle truly add up to 180 degrees, and parallel lines will never meet, just as we learned in school. This simple fact is profoundly puzzling. For the cosmos to achieve this precise geometric balance is like finding a pencil that has remained perfectly balanced on its tip for billions of years. Any tiny initial imperfection, any minuscule deviation from this perfect state, should have been wildly amplified by gravity over billions of years. A universe born even slightly too dense would have collapsed back on itself in a dramatic reversal eons ago. One born with a little too little density would have expanded into a thin, cold, and featureless void almost instantly. Our existence seems to hinge on a preposterously fine-tuned starting condition, a coincidence so unlikely it defies belief. Cosmic inflation provides the elegant solution. That period of hyper-expansion acted like a cosmic iron, smoothing out any initial wrinkles in the fabric of space-time. Imagine the surface of a crinkled piece of paper. If you could stretch that paper to the size of a continent, any small bumps or curves would become imperceptible. The surface would appear perfectly flat to anyone standing on it. This is what inflation did to the cosmos. It stretched space itself so enormously that any primordial curvature was smoothed into the flat geometry we measure today. This process locked the universe into a state of critical density, the precise balance point between eternal expansion and eventual change. The observed flatness is therefore not a mysterious accident. It is a direct and natural prediction of inflation, a required outcome of that brief, powerful stretch. This elegant resolution to the flatness puzzle is deeply connected to another fundamental mystery of the cosmos, one that concerns the very nature of nothingness itself. This cosmic flatness and the grand structure of the cosmic web are not the only profound mysteries solved by that initial hyper-expansion. Another, perhaps more baffling, puzzle is written across the entire sky, a problem of connection known as the horizon problem. Why does the universe look so remarkably similar in every direction we look? The ancient cosmic microwave background radiation has a nearly identical temperature everywhere, with variations of only 1 part in 100,000. This would be unremarkable if the entire sky had once been a single, cozy room where warmth could easily spread and even out. But the standard Big Bang model presents a serious challenge. When we look at two opposite sides of the observable universe, we are seeing regions that are separated by nearly 93 billion light-years today. Yet the universe is only 13.8 billion years old. In all that time, light has not had nearly enough time to travel from one of these regions to the other. According to the old model, these distant parts of the cosmos should have never been in contact, never had a chance to exchange warmth or reach a common temperature. It is as if you walked into a vast global auditorium and found that every single person from the front row to the very back had the exact same body temperature to a tiny fraction of a degree without ever having communicated. This seems impossible. Cosmic inflation provides the elegant and necessary solution. It tells us that the entire observable universe, everything we can possibly see, was once contained within a region vastly smaller than a single proton. This subatomic speck was in a state of perfect thermal balance, a single, well-mixed and uniform entity. Then inflation occurred. That unimaginable stretch did not just create a lot of space, it took that tiny, connected region and expanded it to a size far larger than our entire observable horizon today. The uniformity we see across the sky is not a coincidence, it is a preserved relic of that initial closeness. The entire cosmos was once a single, tiny neighborhood before an expansive growth spurt sent its different parts flying apart, forever preserving the memory of their shared origin. This explains the large-scale homogeneity in a way the standard Big Bang alone never could. With these immense, cosmic-scale puzzles now elegantly resolved by a single, brilliant idea, our focus can shift to a more intimate scale. The journey from a subatomic speck to a flat, uniform universe is only half the story. The true magic lies in how that perfect uniformity was subtly and beautifully broken by the smallest of things. The specific strength of those quantum ripples was not arbitrary, it was a cosmic necessity. The amplitude of these primordial fluctuations was incredibly small, a mere 1 part in 100,000 variation from the average density of the early universe. This seemingly insignificant number was in fact perfect. It landed in a narrow window of viability that allowed our complex cosmos to emerge. Had the fluctuations been any weaker, the story of the universe would have been one of eternal silence. The subtle density differences would have been too faint for gravity to gain any meaningful foothold. Matter would have remained a nearly uniform, dispersing haze, forever preventing the collapse of gas clouds into the first stars and the assembly of majestic galaxies. No stars would have ignited, no planets would have coalesced, and the cosmos would be a vast, dark, and structureless expanse. On the other hand, if the quantum jitters had been significantly stronger, the universe would have faced a dramatically different and equally barren fate. Gravity would have acted with ferocious speed, causing matter to catastrophically collapse directly into immense black holes. There would have been no graceful dance of galaxy formation, no steady fusion in stellar cores, no billions of years of stable cosmic evolution. The universe would be a collection of gravitational monsters in an otherwise empty void, with no possibility for the delicate processes of chemistry or biology to ever begin. The fact that we observe a universe filled with galaxies, stars, and planets tells us that the fluctuations generated during inflation were precisely tuned for complexity. This Goldilocks condition, not too smooth and not too lumpy, is one of the most profound mysteries in all of science. Why did the inflationary engine produce fluctuations of exactly this required magnitude? Some physicists suggest this fine-tuning might be a clue pointing toward a multiverse, a vast ensemble of universes each with different physical parameters, and we simply inhabit one of the rare ones where conditions were just right for life. Others seek a deeper, fundamental principle that would naturally dictate this specific value. This delicate balance forces us to confront the very nature of the vacuum from which everything emerged, a quiet realm whose subtle quantum fizz held the precise blueprint for all of existence. The quietest, most empty space you can imagine is not truly empty at all. Underneath the apparent stillness, the quantum vacuum is a vibrant sea of activity. According to our best theories, what we call a void is actually filled with fleeting events. Pairs of particles and their antimatter twins constantly flicker into being, emerging from borrowed energy, only to fade back into the background an instant later. This endless dance is not just a theoretical curiosity, it has a tangible effect on the cosmos. It creates a background energy permeating all of space, a pressure known as vacuum energy. Today, this latent energy manifests as the mysterious force we call dark energy, which is causing the expansion of our universe to accelerate. This modern vacuum energy is incredibly faint, a mere whisper compared to the roar of its primordial ancestor. During the epoch of inflation, the vacuum energy associated with the inflaton field was unimaginably more potent. It was this specific, high-energy state of the vacuum that powered the exponential stretching of space itself. The very same quantum jitters that seeded the galaxies were a direct product of this restless vacuum. Those fluctuations were the tiny, temporary bubbles of energy that appeared and were then stretched to cosmic proportions. This forces a complete redefinition of nothingness. The cosmos did not emerge from a sterile, philosophical void, but from a state brimming with latent potential, a fundamental energy intrinsic to the fabric of reality. The line between something and nothing becomes beautifully blurred, revealing that our entire universe could be the amplified echo of a quantum hum. This profound connection between the vacuum and everything we see points toward an even more staggering possibility, one that suggests our cosmic home may be far from unique. This quantum randomness, the very force that seeded our galaxies, also contains a startling implication for the cosmos as a whole. The graceful exit from inflation, the moment the inflaton field rolled down its energy hill, was not a single, synchronized event across the entire universe. It was triggered by local quantum jitters, and by their very nature, such fluctuations are unpredictable and uneven. In most of the primordial cosmos, the field decayed, ending inflation and creating a hot Big Bang universe like our own. But in some rare, statistically inevitable regions, a different quantum roll of the dice occurred. There, the fluctuations happened to keep the inflaton field perched on its high-energy plateau. In those pockets, the repulsive gravity of the false vacuum remained in control, and the frantic exponential expansion of inflation never stopped. While our local bubble of reality was settling into the cosmos we know, these other regions were continuing to inflate at a staggering rate, generating more and more space, and within that new space, the same quantum process would inevitably create other, isolated bubble universes. This is the theory of eternal inflation, a self-replicating cosmic engine where inflation, once started, never truly ends, but instead spawns an infinite multiverse of disconnected cosmic domains. Each of these bubbles represents a universe with its own unique local laws. The random nature of the quantum fluctuation that ended inflation within a bubble would determine the specific properties of its vacuum, effectively setting the values of its fundamental constants and forces. In this grand vision, our universe is not the cosmos, but merely a single room in an infinite cosmic hotel. The strength of gravity, the mass of an electron, the very number of spatial dimensions we experience, all of these could be different in other bubbles. Some universes might be stillborn, collapsing instantly or expanding too rapidly for structure to form. Others might be vast, empty voids. Our universe, with its specific, life-permitting constants, is not necessarily a miracle of fine-tuning, but could simply be a statistical inevitability. In an endless multiverse, every possible combination of physical laws will be realized somewhere. And we, of course, find ourselves in one of the rare bubbles where conditions allowed for stars, planets, and life to emerge. This idea, while currently beyond our observational reach, is a direct and natural consequence of uniting inflationary cosmology with the inherent randomness of quantum mechanics. It transforms our picture of reality from a single, finely tuned symphony into one movement in an endless, chaotic, and creatively fertile cosmic orchestra. Beyond the faint density ripples that seeded the galaxies, inflation's most profound echo would be written not in matter, but in the very geometry of reality. It should have generated a background of primordial gravitational waves, ripples in the fabric of spacetime itself. These are not like the density waves that traveled through the cosmic plasma, but tremors in the stage upon which the cosmic drama unfolds. To understand their significance, picture the early universe as the surface of a vast, turbulent ocean. The density fluctuations were like the gentle swells and troughs on the water's surface. The gravitational waves, however, were the deep, resonant vibrations that shook the ocean basin itself. These space-time ripples are a direct probe of the incredible energy of the inflationary expansion. Their strength is tied directly to the energy scale of the inflaton field, offering us a way to measure the raw power of the universe's first moment. The challenge, of course, is finding them. These primordial waves are incredibly faint, having traveled for nearly 14 billion years. They left their most promising signature not in temperature, but in the polarization of the cosmic microwave background light. As this ancient light traveled through the seething spacetime of the infant cosmos, the gravitational waves would have gently twisted its orientation, imprinting a specific, swirling pattern known as B-mode polarization. Finding this unique curl in the oldest light is considered the ultimate confirmation for inflation. The search for this signal is a story of human ingenuity and cosmic patience. In 2014, the BICEP-2 experiment announced a possible detection, a moment of immense excitement for the scientific community. Further analysis, however, revealed that the signal was largely, if not entirely, caused by interstellar dust within our own Milky Way galaxy, a sobering reminder of the immense challenge of this measurement. Yet the quest is far from over. A new generation of incredibly sensitive telescopes, both on the high, dry plateaus of the Atacama Desert and in the pristine silence of space, continues the hunt. They scan the sky, meticulously subtracting the foreground dust to listen for the faintest whisper of that primordial tremor. To detect these waves would be to peer directly back to a time when the entire cosmos was smaller than a single atom, to witness the moment space itself was being stretched beyond comprehension. It would open a window into physics at energies 1,000,000,000,000 times greater than what our most powerful particle colliders can achieve, revealing secrets about the fundamental forces that we can currently only dream of. This relentless search pushes the very boundaries of our observational capabilities, a testament to our deep desire to understand not just what happened after the beginning, but to glimpse the very first moment of existence itself. While cosmic inflation has reshaped our understanding of origins, its very success invites a healthy dose of scientific scrutiny. A key challenge lies in the theory's remarkable flexibility. With adjustments to the properties of the inflaton field, cosmologists can produce a vast landscape of possible outcomes, from a perfectly flat universe to one with more pronounced wrinkles. This ability to explain almost any observation raises a critical question: could the theory be too adaptable to ever be proven wrong? This has led some physicists to explore entirely different frameworks for the universe's first moment. One compelling alternative is the bouncing cosmos model, which suggests our universe is not the first, but merely the latest in an endless cycle of expansion and contraction. In this view, the Big Bang was not a true beginning from a singularity, but a powerful rebound from a previous universe's collapse. Another idea, the emergent universe scenario, proposes a cosmos that has always existed in a near-static state, only gradually transitioning into the expanding reality we see today. Both of these concepts aim to avoid the perplexing singularity and the need for a unique starting point. Meanwhile, more fundamental theories like string theory and loop quantum gravity attempt to derive the conditions for inflation from first principles, seeking to explain why the inflaton field should exist at all and how it connected to the particles that followed. The details of reheating, that spectacular moment when the inflaton field transformed its energy into the hot plasma of the Big Bang, also remain largely in the realm of theoretical speculation. These challenges are not weaknesses in the scientific process, they are its greatest strength. The vibrant debate between competing ideas pushes cosmologists to devise sharper tests and more precise measurements. It ensures our picture of the cosmos remains dynamic and self-correcting, constantly refined by new evidence and deeper questions. This critical perspective is vital as we prepare for the next generation of experiments, designed to probe the very limits of what we think we know about our cosmic dawn. The hunt for the universe's first tremor is entering its most ambitious phase. A new generation of observatories, both in the silent vacuum of space and from the world's highest peaks, is being built with one primary goal: to find the faint, swirling polarization in the cosmic microwave background that would be the definitive signature of primordial gravitational waves. Space missions like the upcoming Light-Bird satellite will scan the entire sky from beyond the interference of Earth's atmosphere, while immense ground-based arrays like the Simons Observatory and the future CMBS-4, with their hundreds of thousands of detectors, will achieve a sensitivity once thought impossible. These instruments are so precise they are essentially measuring the universe's earliest imprint, but the search does not rely on a single line of evidence. In parallel, powerful new telescopes are turning their gaze to the large-scale structure of the modern universe, the European Space Agency's Euclid mission and the Vera C. Rubin Observatory's legacy survey of space and time will map the positions and shapes of billions of galaxies across cosmic history. This vast, three-dimensional cartography of the cosmic web provides an entirely independent test. By tracing how gravity has sculpted these galaxies over eons, scientists can work backwards to infer the exact pattern and strength of the initial quantum seeds, cross-checking the story told by the ancient light. This global scientific endeavor represents a monumental step in our quest for origins. The data collected over the coming decade will deliver a clear verdict, either confirming the inflationary paradigm with undeniable proof or revealing a surprising inconsistency that invites us to reconsider our entire cosmic origin story. As these telescopes peer deeper into the void than ever before, theoretical cosmologists are refining the possible models of inflation, preparing for a future where we will not only know if inflation happened, but precisely which version of the event shaped our reality. The identity of the inflaton field remains one of cosmology's deepest secrets. We have a magnificent framework for what happened in the universe's first moments, but we still do not know what the engine itself was made of. This is the great frontier, the search for a microphysical model of inflation. Is the inflaton a brand new fundamental particle, one predicted by elegant theories like supersymmetry? Could it be a close relative of the already famous Higgs field, the entity that gives other particles their mass? Or is it something entirely unexpected, a new kind of cosmic substance that operates only at energies we can no longer directly access? The ultimate ambition is to anchor this cosmic story in a deeper bedrock, to derive the inflaton and its behavior from a complete theory of quantum gravity. This is the realm of string theory and its competitors, where physicists seek the laws that govern the Planck epoch. That was the very first sliver of time, a duration so short it is a decimal point followed by 43 zeros and a 1, when the universe was so small that gravity and the other forces were woven together. In that early phase, the inflaton field must have somehow emerged. Building this bridge is one of the most difficult challenges in all of science. It requires a perfect marriage of cosmology, which describes the vast universe, and particle physics, which describes the tiniest components of reality. Success would mean a single, seamless narrative, a story that flows without a break from the quantum fizz of spacetime itself to the grand architecture of the cosmic web. This quest to unify the very small with the very large brings us back to a profound and humbling insight about our place in the cosmos. Our magnificent cosmos, with all its splendor, seems to ask for an equally magnificent cause. Yet the origin story written in the quantum static and ancient light points toward a different, more subtle truth. The primordial void was not a sterile emptiness. It was a state of profound potential, guided by the unwavering principles of quantum physics. This invites a complete rethinking of what we mean by nothing. The quantum vacuum, with its fleeting particles and latent energy, is far from nothing in a philosophical sense. It is a something with specific properties and behaviors. For some, this realization resolves a great mystery. If a universe can naturally emerge from the restless activity inherent to space itself, the need for a separate, external agent of creation fades. The cosmos becomes a self-contained story, with its beginnings written into its own fundamental operating principles. For others, however, this simply moves the ultimate question back one step. Where did the quantum laws themselves come from? Why is there a quantum vacuum with the potential for expansion at all? This line of inquiry leads to a deep connection between law and existence. It suggests a universe that possesses a set of consistent rules may be one that naturally gives rise to its own material content. The laws themselves become the fertile ground from which everything else emerges. This ongoing journey of discovery is not just about finding our starting point. It is about understanding our ongoing place in a cosmos that is still revealing its deepest nature, a reality where the line between nothing and everything is beautifully and perhaps permanently blurred. The destiny of our universe was locked in place during those first fleeting moments. The incredible velocity of the inflationary expansion, combined with the precise density of matter and energy created during reheating, set a cosmic course that can never be altered. Think of the universe as a rocket launched from Earth. The speed of its launch and the amount of fuel it carries determine whether it will achieve escape velocity and journey into the void forever, or if gravity will eventually win, pulling it back in a dramatic return. Our cosmic rocket was given a very specific push. The initial expansion rate and the total density have placed our universe on a very particular trajectory, one that points toward an unending future of growth. Current observations of distant supernova and the cosmic microwave background reveal a startling truth. The expansion is not slowing down as once expected, but is actually accelerating. This points to a future of perpetual expansion, where galaxies will continue to recede from one another across an ever-widening gulf. Over trillions of years, the star-forming fuel will be exhausted. The lights of the galaxies will fade one by one, and the cosmos will grow profoundly cold and dark. This distant future is driven by a mysterious force we call dark energy, and here lies a profound and elegant connection. The dark energy accelerating the universe today behaves in a way that is deeply reminiscent of the inflaton field that powered the universe's birth. Both represent a form of energy intrinsic to the vacuum of space itself, a pressure that drives space apart. It appears that the same type of physics that ignited the cosmos in a flash of hypergrowth may also be guiding its long-term fate. This means that by studying the origin of everything, we are also reading the final chapter. The story of our universe, from its first quantum tremor to its last fading ember, is a single, continuous narrative. We exist in a special moment, a bright and vibrant era nestled between the fire of the beginning and the quiet of the end, granted a privileged view of the entire cosmic story. This apparent fine-tuning of the universe, from the strength of gravity to the precise amplitude of those quantum seeds, leads us directly to a profound and often debated idea, the Anthropic Principle. In its simplest form, it suggests that the universe we are capable of observing must be compatible with our own existence as conscious observers. We should not be surprised to find ourselves in a universe with the right conditions for life, because in a cosmos without those conditions, we would not be here to ask the question in the first place. This is not so much an explanation as a logical statement of our situation. Yet when viewed through the lens of eternal inflation and the multiverse, this principle takes on a powerful new meaning. The apparent fine-tuning may not be a mysterious coincidence at all, but a simple consequence of statistics in an unimaginably vast reality. If the multiverse is real, then every possible combination of physical constants and initial conditions is realized in some pocket universe. An infinite number of cosmic domains would not develop further, collapsing instantly or expanding into featureless emptiness. Others might be filled with fleeting, unstable particles or possess forces too weak to ever form atoms. Our universe, with its specific, life-permitting numbers, is simply one of the rare habitable bubbles. We are not witnessing a cosmos designed for us, but rather finding ourselves in the one type of cosmos that could ever have produced us. This perspective grounds the specialness of our existence not in purpose, but in the impersonal and random outcomes of a fundamental physical process. It connects the grand physics of cosmic inflation directly to the intimate fact of our own consciousness, suggesting that we are a natural, if exceptionally rare, product of a vast and creative cosmic landscape. The creation of the cosmos demanded more than just space. It required the raw material for everything to come. This is where the story of cosmic inflation converges with the standard model of particle physics, our catalogue of the universe's fundamental building blocks. That spectacular moment of reheating when the inflaton field released its pent-up energy was the ultimate forge. It was not just heat that filled the newborn universe, but a brilliant, dense broth of the first true particles. From the decay of that single, primordial field emerged the quarks that would later bind into protons and neutrons, the lightweight leptons like electrons, and the ghostly force carriers such as photons. This was the moment the cosmic stage was populated with the actors for all of physical reality. Yet this process presented another profound mystery. When matter is created from pure energy, it is always produced in pairs, a particle and its antimatter counterpart. These opposites should have immediately annihilated each other upon contact, leaving behind a universe filled with nothing but radiation. The fact that we live in a cosmos dominated by matter means that a crucial, one-sided transformation must have occurred. During reheating or immediately after, a process known as baryogenesis must have favored the creation of matter over antimatter by the tiniest fraction, one extra particle for every billion annihilations. This imbalanced recipe is what allowed any lasting structures, including us, to exist at all. The incredible energies present during inflation itself offer our best chance to understand how this could happen. They probe realms far beyond what the standard model can describe, touching on ideas like grand unification, where the fundamental forces merge into one, or supersymmetry, which proposes a hidden partner for every known particle. The quest to understand our cosmic origin is therefore inseparable from the quest to understand the rules that govern the smallest pieces of reality. The largest questions we can ask about the universe are written in the language of the very small, a beautiful synergy that drives the most ambitious experiments in physics today. This grand narrative reveals a universe that taught itself how to build, from an origin of supreme simplicity, governed by a single dominant force and the basic rules of quantum chance. The cosmos embarked on an irreversible journey toward diversity. That initial, featureless state held within it, like a seed, contains the blueprint for a tree, the potential for every galaxy and every living world. The mechanism was one of amplification. The simple, random flicker of a quantum fluctuation was not a detail to be smoothed away, but the essential first ingredient. Cosmic expansion stretched this minute imperfection. Gravity patiently sculpted it over billions of years, and the result was a cosmic web of such intricate structure that it now contains conscious beings capable of tracing their own lineage back to that first tremor. The emergence of life and mind is not an alien event in a cold universe, but the most recent and sophisticated expression of this deep, creative impulse woven into the fabric of reality from the very first moment. We are the universe becoming aware of itself, a natural consequence of simple rules playing out across an immense stage of space and time. This perspective does not diminish our existence, but rather grounds it in a story more magnificent and interconnected than any myth. Our search for meaning is itself a product of the same cosmic evolution that built the stars. As we near the end of our exploration, we are left to reflect on what this entire journey, from the quantum beginning to the conscious present, ultimately signifies for our understanding of reality itself. Our journey has taken us from a subatomic realm of pure potential to the magnificent cosmic web we call home. This entire epoch, from the first stars to the spiral of our own galaxy, traces back to a single, breathtaking idea, a moment of hyper-expansion known as cosmic inflation. We have seen how the faintest quantum static, the random fizz of the void itself, was stretched by that ancient growth into the cosmic blueprint for everything. The evidence is written in the oldest light in the universe and etched into the vast, clustered distribution of galaxies across the great expanse. This single framework elegantly untangles the deepest puzzles of the cosmos, explaining why our universe is so remarkably flat and why its most distant corners share a common temperature, as if they were once intimately connected. Of course, profound mysteries remain. The true identity of the inflaton field is still unknown. The search for primordial gravitational waves continues, and the staggering possibility of a multiverse hangs on the edge of our understanding. Yet through it all, the inflationary paradigm stands as our most powerful and compelling origin story. It forges an unbreakable link between the unpredictable quantum realm and the grand scale of the cosmos, revealing a universe capable of generating its own splendid complexity from the restless energy of what we might call nothing. So take a moment to reflect on this. Every atom that makes up your body, every element forged in stars that shone long ago, was once part of a microscopic quantum fluctuation in the very first instant of time. Your existence is a direct echo of the cosmos learning how to build. If this journey through the origins of everything has expanded your mind, we would love to hear your thoughts in the comments below. Be sure to subscribe for more deep dives into the wonders and mysteries of the cosmos.